Well, thanks for inviting me, and thank you everybody for coming here today. Here we go. Um, well, Today I'm going to talk about what I've been doing for the past couple of years, which is making a language that is a C++ replacement. And you might ask, why would you ever want to replace C++? And maybe a lot of people know the answer to that already. The answer is that C++ is a really terrible, terrible language. So it would really help us to get off it as quickly as we can. But here's the funny thing, right? Despite the fact that it's such a terrible language, games use it. If you talk about lower end games, there's games obviously in browsers or that use C# or something. But the highest performance games that render the most impressive things and have the most complex simulations all use C++ still. It's the year 2018, right? C++ is from the 1980s. It's been modified a little bit, but the idea for the language was come up with in the 1980s. So why do we still use it? And the answer is because despite as terrible as it is, it still does something right that's very basic that almost every other language that's been made since then actually gets wrong. So I'm going to talk about some wrong ideas that have been happening for the past few decades. I'm going to start with maybe what is the most basic one. This is an attitude that I think came out of academic circles, but it's percolated through industry and it's everywhere now. And it's an idea about, okay, what should a language help you do? It should help you be a more powerful and expressive programmer who can get more things done quickly and they work better. And how do you do that? Well, there's some kind of idea that's like climbing to heaven or something, where like the language lets you express higher and higher level things, and we don't care about like implementation details, like where memory comes from or how much time things take really, except in very broad scoped algorithmic measurements. Because implementation details are complicated to think about and they slow you down. And if you didn't have to think about those implementation details, that's much less work to do and you're more productive. So the idea here is that, somehow the job of a programming language is to put you in some kind of magical space where you're just programming with magic and clouds and daydreams. And stuff like managing memories or managing memory you don't think about, like what your data structures even look like, you don't need to know, and all that stuff. And the way that I've stated this, it's obviously making fun of the idea a little bit, but this idea, I think, underlies most programming language designs from the past few decades, and it's wrong. But despite the fact that it's wrong, there's been some success with it. Starting in the 1990s, I chose the year 1991 a little bit arbitrarily, but sometime in the 1990s, we started having this trend of a whole bunch of interpreted languages happening. So like Perl and Python and all these things. Because the idea was like, hey, we want to make things that are high level. C is like a low level compiled thing. Interpreted languages like Lisp are high level, so we're going to do things like that. And you know what? Computers are fast enough that it's not going to matter. You're just going to run your script and it's fine. It's just going to run interactively fast and nobody will care what language it's in. But because our language is going to have all these high level features, it's going to make you a more productive and powerful programmer. So that was the idea, and it actually sort of succeeded for a while, right? But it caused a problem because, well, let me go back and talk about another kind of language for a second, right? So one kind was the scripting language, and another kind is what Microsoft has since then called the managed languages. This maybe starts with things like Java, and has since proceeded to things like C# and whatnot, where it's supposedly a compiled language, but you have a very heavy runtime that imposes performance costs. Maybe it's garbage collected or something, but it also has a lot of opinions about what your program is allowed to do and about what implementation details of the machine it's allowed to play with, right? So those are sort of the two major categories of things. And something happened where, all these languages got made, and they actually do have higher level features that help you do things faster, right? They also are pretty slow languages. And because these things have been correlated again and again in these examples that we've seen over the years, Many or most people, I would say, believe, or maybe not even believe, but just in their mind, there's this conflation between languages being slow or giving you a lack of control over what's happening, and those languages being powerful and expressive and giving you high-level ability to manipulate things. And that's not actually true. Those two things are actually mostly orthogonal. So for example, you can have a language with most of the features of C#, but that's as low level as C at the same time. It's just nobody's really made that, and so we've never seen that example, and so our brains don't really understand it, right? Here's another idea that's wrong that most of the world labors under, and I'm sort of thinking of it as climbing to heaven part 2. There's some weird idea that more layers of software is a good thing, right? So like somebody makes some code like in a library that does some job, and then I'm going to make my library that's like a wrapper around their library, and it's mostly just going to call their stuff, but I'm going to add like 10% on the side, right? And now you can use my library instead of their library, and then somebody else comes along and adds like another 10%, right? And you start stacking these libraries enough, and then that's not even enough. So like now let's make a program that uses all these libraries, but like the program itself will not really do the whole job. It'll like talk to other programs on the same computer over like local sockets to do the rest of the job, and each of those programs will have all its libraries, right? And the idea that people have is like you stack up these layers of code and it gives you something better and better, right? But I think that most of us know, who have done a lot of real work, that what you get in that case is not really better and better. It's actually worse and worse, right? Because the stack is not a well-constructed thing. It's like wobbly, right? And if you try to climb up on it, it's going to just like fall over and dump you on the floor, right? So the more layers of software you have, right, the more software you have, the harder it is to understand, the harder it is to be clear about what the interactions are between all the layers for you as someone who wants to debug or modify this, but also for the people who wrote it originally, right? So these layers don't generally couple together perfectly. They're sloppy, right? They move. There's lots of times when you're not sure what's really going on, and those are magnified as you have more and more layers. And then also, of course, more layers take longer to compile and all those usual problems. There's a lot of other weird assumptions. This one isn't exactly about language semantics anymore, but people have this idea that in the modern world, if you're going to program, you need this complicated, slow, buggy thing called an integrated development environment, like Visual Studio or Xcode, that gets between you and the act of programming, right? So like you can't like program without this thing, the job of which is, I don't even know what the job is, right? Because it's like, it's not exactly the debugger. The debugger is a separate thing, but like it lives there. It's not really the editor because you can use a separate editor. It's like the thing that knows what files are in the project or something. It's a weird Frankenstein's beast, actually the main job of which is to make up for the fact that a lot of languages are underspecified, and I'll say exactly what that means soon. But people have this idea that you need this thing. And in fact, I think the value of this thing is very close to 0, or it's actually negative because it gets in your way so much. The actual value is in the debugger and the editor, right? The IDE is just a giant piece of junk, in my opinion. People also have another weird idea that a programming language should be like a grand ecosystem, and if you're going to come up and start using it, then you're entering the ecosystem and you get to learn about all these crazy things. Not even just about languages, actually. Anything now. So I was at the GDC this year, and I was in the presentation about the Vulkan graphics API, right? And the guy puts up this slide, multiple slides actually, talking about the Vulkan ecosystem, and he has all these boxes with lines between them, and there's like funny names of what all these like different things are in the boxes, and I'm just like, oh my God, like you just killed all enthusiasm I had for learning about this thing. I don't want to learn an ecosystem for a year. I want to just put 3D graphics on the screen, right? So like actually if somebody is making a system that's good for you to use, it's as simple as it can be while enabling you to do the job. It doesn't force you to like learn all sorts of obtuse stuff in order to do a job. But somehow people are stuck in this mindset that that is what it's supposed to be. You know, it's like when you have a division of a company or a government, and it used to have a real job, but now its job is to perpetuate itself and make itself bigger, right? That's like what all software projects are now. And it's really sad. So we're getting to smaller and smaller points here, but one common one that maybe C++ programmers are much more familiar with, there's all these people saying, if you're going to be a good programmer in these languages, you should use this thing called RAII, right? Or in some other languages like Swift or something like, use ARC, automated reference counting, because it takes care of your memory for you and all that. And that makes you a good programmer, and you don't have to think about these details, and you have fewer bugs, and you have more memory safety and all that. And it's like, okay, you could do that stuff, but the cost is actually tremendous, right? When you do that stuff, your program ends up 100 times slower than it should be, maybe more. And people who are proponents of these techniques will get very upset as soon as I say that, because they're like, no, 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 RAII, like the constructor, destructor, they inline, they don't generate that many instructions, like the reference count for ARC is just, that can get optimized out a lot of the time, and even when it doesn't, it's small. But that's beside the point, because the problem isn't the instructions that are generated at all. The problem is not the actual code. The problem is that conceptually, when you program in this way, you are thinking about the things in your program as a bunch of tiny little isolated units that live in random places on the heap. Because like if you've got a reference count and it's going to go to 0, what happens? Well, it gets freed. What does that mean it gets freed? Well, just somewhere on the heap is now available for other memory to go. Well, what does that mean? Well, when you're navigating these data structures then, they're scattered across the heap. And what does that mean? It means you're going to miss the cache a lot, right? So the difference in performance between an L1 cache hit and a miss that goes all the way out to main memory is a lot more than 100 times, actually. It's several hundreds on most modern CPUs. So saying that your software is only going to be 100 times slower if you do these things is kind of giving you the benefit of the doubt that you like worked in some other optimizations along the way. But it doesn't just make your code slower, it makes it harder to understand, right? Like, a lot of the times, there are things associated with the destruction of a resource that are important for program correctness. Like, I need to know when this file is closed, because the next step of my program can't validly happen until I know that that's true. If you start hiding things like that inside, like, well, we reference counted this thing and it went to 0, and when it goes to 0, the file closes, you don't really know anymore when the file closed. Or maybe the person who originally wrote the program did, and now you're coming along looking at it and you're like, I have no idea what's going on because this is not explicit anywhere, right? Even if that was you who wrote it like 3 months ago. So being explicit about things that are important is good for software quality, and hiding those things is bad for software quality. Okay, so I could actually go on for a long, long time just listing more and more of these things that are supposedly common knowledge about how to program well that I think are completely wrong. But I'll just stop listing them because we have a lack of time, and I'll just say, well, when somebody sits down to design a programming language, they're doing that because they want to help you, right? They want to, well, I mean, sometimes. But giving the benefit of the doubt, right? They want to help you. They want to make a thing that helps you program in the good way, the way that's going to be productive. And the problem is that they have all these wrong ideas about what that good way to program is, right? And so if you have an idea that's different from that about how to program, you can't actually use the languages designed by these people, actually not most of them, because you'll end up fighting the language all the time, because the language is built to support a certain type of programming that you don't necessarily want to do. And that's actually why we still use C++ today, because C++ actually lets you, it doesn't put so much of a runtime in the way that it doesn't prevent you from doing very specific low-level things when you decide that you need to do them. Of course, the language is still evolving over time, and it's getting crazier and crazier, but at this point, it's still kind of okay. But so if all that stuff is wrong, then what's right? And I can maybe answer that starting at a very general, high level. Well, what should we care about? Well, I think first, quality of life of the programmer, right? The programmer should be happy doing programming, because that's why most of us got into this in the first place. We shouldn't be miserable like many of us are so much of the time. People are laughing because it's actually true. Like, we know that's true. So what is quality of life? Well, like, you know, you're not spending all your time doing stupid bullshit all the time, right? Like you're doing exactly the thing you want to do, and it works. And when you make a mistake, it's not that hard to figure out what the mistake was and so forth, right? Second, simplicity, right? Because you have something you want to do. You don't want to have to learn all sorts of, or at least I don't want to have to learn all sorts of unrelated things before I can then turn around and do the thing that I was trying to do, right? And if I'm trying to debug a program, debugging is thinking about all these degrees of freedom of what might be going wrong and like somehow picturing in your head, this is probably what happened, right? That's what hard problem debugging is like. And the more complicated the system is, the more things there are to think about and the less of an idea you have about what's going on. Also, the more complicated the program is, the harder it is to get it to do exactly what you want, right? So simplicity is good. And then again, expressive power is good. So if you can, with a small amount of code, build a large amount of functionality in a short time, that's all great. So this is what I think is important. Now, of course, the problem is, if you ask the people who made the other languages that I was just complaining about what's important, they would probably say a list something a little bit like this too. It'd be a little different, but I think we mostly agree. So the disagreement is not at this high of a level. The disagreement comes in a little later on when we start converting these high-level ideas into more concrete implementation details. So it's important to do that conversion into implementation details well, right? Because my claim is if you do it badly, you end up back in the soup of all the problems that I was talking about. But if you do it well, I think huge increases in productivity and efficiency are possible. I used to, when I was starting this project, think that I had a very realistic attitude, and I was like, okay, 10%, maybe 15% efficiency increase in terms of number of hours it takes to do anything. That would be amazing, and that's probably the best I could hope for. And if you imagine that every single programmer in the entire industry saved 10% of their time, like if you calculated the dollar value of that, it would be just insane, right? It would be a very large number. These days, I think much more than that is actually realistic, now that I'm very deep into the problem and see it very well. I think 50% is possible. 80% may be possible in the further future, which would be just astonishing. And the fact that I see that such things are possible makes me a little bit sad that it seems like everybody is sort of going in the wrong direction language design-wise. I'm not making the claim that we are close to providing 50% efficiency increase. I think we're more around 15 to 20% right now, but we're going to be aiming for 50% eventually. Okay, so if I said this like climbing to heaven idea is a bad one, then what's a better idea? Well, it's not that like climbing to heaven is necessarily completely wrong. It's just that it's an incomplete idea. Because the thing about that climbing is you sort of leave the ground behind and you have disdain for what's on the ground. I don't care about implementation details. I don't care about all this stuff. The problem is we program real computers in the real world, and those computers are on the ground, right? How fast they run depends on very real implementation details that we need to know and care about. How robustly they run also depends on implementation details like that, right? And so what's maybe a better idea is you want to reach up so that you can do these abstract things when you want to, but you still want to stay on the ground so that you have the ability to manipulate things down there. So you actually want to go both directions. So I would say that one of the flaws that was made is that in the past, people thought expressive power just means ability to express high-level things. But you need to be going in both directions. You need to be able to express high-level things, but you also need to be able to get very specific about low-level things at the times when you care about doing so and when you think it's important, and hopefully only those times, right? Both directions. And then you can really get some real work done. So all of this is just my way of answering this question that I get a lot. Like, why would you ever make a new programming language? Oh my God, there are so many programming languages in the world. Why don't you think you can just use one of those? And again, the answer that I have is that almost every one of those languages buys into these assumptions that I listed and then several others that I didn't, that when you put them together prevent you from writing programs that run efficiently or that are clear or that are brief and concise and easy to understand. And so if you want to do work that's not like that, you kind of have to make a new language. All right. So we've been working on this compiler for a while. I started it in 2014 as a part-time project because I was working on a game. In 2016, we shipped the game, and in the middle of that year, I switched to full-time on the compiler. Now we have 4 people working on it. And 2018 has sort of been a time of re-engineering. So prior to this year, we had been experimenting with high-level features and figuring out what is the general shape of this language and sort of trying wacky stuff. And at this point, we've got most of the wacky stuff nailed down. And this year I said, okay, now that we basically know what the language is, I'm going to go back and like rewrite large parts of the compiler, because when we wrote these, we had no idea what we were doing. Well, we knew what we were doing, but we didn't really know where it was going. And so now that we do, we're making it more robust and stuff and fixing bugs and all these things. But we're not just making a compiler, we're making a game, because we have to prove out the idea, right? So we're making a commercial game. It's going to ship on several platforms, Steam and a couple of consoles maybe. We haven't decided exactly what the platforms are. Oh, and like Linux and Mac. That game, you know, I demoed it last year, and it was about 40,000 lines. This year, it's about 80,000 lines. So it's doubled in size in the past year. That's 80,000, including comments and blanks. And it's a little bit of a terse language, so we don't have header files, for example, and other things are just a lot more brief to express than C++, so you could think of it as the equivalent of maybe 110,000 line C++ program or something like that. It's hard to say. And it compiles pretty fast. So this 80,000 lines compiles in under 1 second on my desktop and about 1.5 seconds on my laptop here, which is a little bit slow. But I'll just demo that. So just clear the screen, and I'm going to hit F7, bam, bam. 1.7, that's pretty slow. I don't know what happened. 1.6, slideshow program slowing it down a little bit or something. Anyway, but it's still, you know, second and a half right now. And it's a little bit of an unfortunate time to demo this because, like I said, we're in the middle of restructuring all sorts of things, and so they're a little slower than they've been. They're going to get faster again. But even at this relatively slow speed that the compiler is at, it is still way faster than everybody else's compiler. Try compiling an 80,000-line Swift program, and while it's compiling, we'll have a long conversation about why it takes so long. So now, of this compile speed, actually, there's some big leeches taking up a lot of the time still. So if I go back and look at these times, you know, this took about 1.6 seconds total. The linker took 0.7 seconds. That's us calling the Microsoft linker and just waiting for the result. So the compiler really is about 0.9 seconds. The thing is, we don't really need the linker because, you know, we're doing the equivalent of what you would call in C++ like a Unity build, not to be confused with the Unity game engine, but like the whole project is one compilation unit. So the linker is really like not really doing very much. The amount of useful work we're getting out of it is almost zero. So why it takes 40% of compilation time, I have no idea, except I can refer you to the slides earlier in the project about why all software is terrible. That is in the roadmap for this year. We're going to try to get rid of the linker by the end of the year, at least for debug builds. And then when it comes to the compiler itself, I think we can get about an 8x speed up, not within this year. This year we can maybe get a 2x. And then over the next couple of years, I think we can get up to 8x. Part of that just coming from optimizing in the regular way, just, you know, hey, you know, this thing is slow, let's go see if we can put a data structure in there to make it faster. But then the other part of it is when I did this, right, and I compiled here, that 1.6 seconds that we compiled in is single core performance for the most part, right? We're compiling that 80,000 line program on one core because the compiler is, again, one compilation unit, and most of the compiler is not threaded yet. There's a little bit of the compiler that is threaded, which is Elixir and parser, and I think that might be, I think we might have introduced a bug lately, because we used to lex and parse in like 30 milliseconds. It's too small for you to see, but now it's taking 200 milliseconds. So I think I think we're spending like 0.15 seconds on a bug right now. It's, I wanted to look into it, but then I had to worry about coming and giving this talk. So anyway, the rest of the speed up that is going to come from actually parallelizing the parts of the compiler that take most of the time. And so we hope to get first a 60% or removing 40% of the runtime by removing the linker, and then speeding the rest up about 8x. And so the result is if I get about 80,000 lines per second on a desktop, or I'm getting about 50,000 on this laptop today, the target rate after we do those speed ups is around 1 million lines per second. That's not a fantasy number. I'm very seriously saying that I think that we will hit that. That is for a non-optimized build, right? So like a debug build where you're not worrying that much about the absolute fastest code. If you want to build a release build, it's up to you which options you want to turn on and how much you make the compiler agonize over finding the fastest code. So that will take arbitrarily more time. But 1 million lines per second is our goal for the production compiler that we consider finished. And so why am I talking about all this? Build time? Well, because I think it's a very major factor both in quality of life and simplicity of the work that we do every day, right? Quality of life, if I can try an idea and see the result very quickly, I'm a lot happier, right? If I'm just sitting there for my thing to build because I dared to change something in a header file and now it's like 2 minutes or something, that's a drag. And it slows me down and I can't solve problems as well. But then also simplicity, because if you can compile 1 million lines per second, or even right now for stuff at the size of this game, if you can compile 80,000 lines per second, you don't need an incremental build. And so you don't need to have all these problems that come along with incremental builds, like, Visual Studio thought this file was up to date and it wasn't, so then I was debugging for half an hour just because it got the build wrong. Or we were trying to do an incremental build and for some reason it was corrupted and it took a while and then it told me, sorry, we can't build, you have to clear it and rebuild from scratch. Like, you don't have any of that stuff. And so there's a great feeling of security in, like, I hit the button, the whole program is built fresh, there's no like craplets left over from previous builds, and everything is good. It really, it helps with debugging time because you have one less thing to think about and worry about, like in terms of the number of things that could be wrong. So I'm going to show a demo of the game really fast to sort of give you an idea what it's like. It's a puzzle game, and it consists of many of the screens are these sort of, or many of the levels are sort of one-screen levels, although there's some that are bigger than that. And it's a sort of game where you can run characters around. Do we have audio? I guess it doesn't matter that much, but I don't hear the audio. Anyway, so the puzzles are sort of things like, how do I get this crystal thing out of this room without locking a character in there? So your different characters have different abilities, and whoops, and I have undo for when I make a mistake, right? Yeah, and well, I don't want to get stuck playing forever. It's distracting. So all of the games that I've done for the past bunch of years aren't just the game. It helps us a lot with production to have the editor built into the game. So like we can pop open the editor here, and here's a palette level where you can just sort of pick stuff to put in other levels, or we can just load this level and start messing around with things. Like, hey, I'm going to drag this tree around or this character, and I want to come in here. Whoop, got to steer better than that. I want to come in there and edit the color of this thing, right? So this is sort of just showing where the 80,000 lines have gone. There's a substantial amount of stuff. I never really know what to demo because, I demoed the game last year and it was 40,000 lines. Character animation system with a full animation graph that does like a simple version of blend trees and stuff. The most recent addition actually is pre-computed global illumination. So if you look at the left and top of the screen here, you'll see it's not really flat shaded. It's got some nice baked-in irradiance there that helps it look good. This is a version of the global illumination that we used in The Witness that we shipped a couple years ago, except we're re-architecting it and changing it around in a way that'll hopefully be better. There's other systems, like I have automatic testing built into the game, so like it has a keystroke recording system, so I can test any level that I'm on by hitting this, and we have that for the whole game, so I can just hit that and it'll start playing itself through all these levels. These particular levels don't have graphics yet. Most of the game doesn't have graphics yet. All right. So that's the general idea. It's a real game. It's not a trivial program. It's really just sort of all that I'm trying to get across there. All right. So it being a real game, it has given us a laboratory for testing out certain ideas. Like I was just saying at the beginning of this talk that I think IDEs are junk, and a lot of people may say, what are you talking about? They're great. So one of the things that we've done for this program is getting rid of the need for build tools and all the giant headaches that come with build tools. So this game right now compiles and runs on Windows and Mac and Linux. And to compile the game on any of those systems, all you need to do is run the compiler on the main file. That's it. You don't need a makefile. You don't need anything else, right? We're used to having all, well, and you don't need to adapt all those things on different operating systems every single time, something changes, right? That whole layer of work is gone. The problem here, as I alluded to earlier, is that almost every language, C++ included, is underspecified, right? The C++ standard will tell you all kinds of things about, like, if a variable is a certain type in the middle of a procedure and you like do an operator on that with another variable, it'll specify what happens there. But the C++ standard has nothing to say about, like, what files are in the program, right? Or how do you build the program? It just leaves you to do that yourself and to do it differently on every operating system, and that is a giant pain, right? So one of the things that we have built into the language is this concept that you want to be able to build your program without a hassle, right? So I really wish the text was bigger. Anyway, so here I just have a piece of a file. It's got a bunch of load statements, which you can think of as being kind of like C++ includes, except we don't have header files. These are just other source files. They're the equivalent of a CPP file. But unlike CPP files, order doesn't matter. The compiler just figures out the dependency order for different declarations, so we can include these in whatever order we want. We have static ifs, so this thing that you can see that's indented is an if checking, hey, if we're in developer mode, include all this stuff, right? So these are things that you would usually have to do in Visual Studio, and then in a totally different way in a makefile on another operating system, and a totally different way in Xcode, and it's the same here. It's the same everywhere. Same with linking libraries, although I don't have an example on there. That's not the only way to get source code into your program. You can also, for example, dynamically generate source code. So here, I have an excerpt from the Sokoban game where we troll through the program to find procedures that are meant to respond to key presses, right? Like key map callbacks, or however you want to think about it. And we look those up automatically so that people can refer to them from key map files, right? We don't have to do this manual labor of registering them somewhere. The metaprogram, which we're showing here, registers them for us, right? So in addition to having code that is like your compiled program, you can also designate a metaprogram that runs at compile time in the compiler and controls compilation. And this is a piece of a metaprogram, and what it's doing here is, well, okay, let's start here at the top. This is a small procedure that just says, we're going to use this printf-like function to make this call add keymap proc, which just registers a string for a name of what the keymap binding is with the procedure pointer, right? So that's what this procedure does. And here we're saying, hey, we're going to make a procedure that's called from main that registers all the keymap procedures. So here's the header of the procedure. It takes no arguments. And then for every keymap procedure that we decided to bind, we just add a line to this array called lines that's generated from here. and then we add the closing brace, and we're going to concatenate that all into a string, and then we're going to call this thing called add build string that puts that in our program just like it's a file. And this runs every single time we compile, right? So if you modify a key map proc, it's automatically in there. Now, how did we know what the key map procedures are? Well, the compiler told us, because we can have our metaprogram have conversations with the compiler, essentially, right? So you have a basic loop structure where you can ask the compiler, hey, do you have a message for me? And if the message is you're done, then you can finish compilation. Otherwise, you can sort of fan the message out to different modules, right? So if you're profiling, then maybe the profiler wants to know about this message, and if you're checking for errors, for example, you can build your own error checking routine that enforces your house style. You don't have to rely on compiler error messages. So, we do things like, hey, you can't store an entity pointer in a data structure because, unless it's one of these whitelisted structures, because entity pointers could go away at the end of the frame, and you don't necessarily know that, right? So we check for that, and we give you an error if you try to do that, and that's not something you would ever build into a compiler. The compiler knows nothing about that, but you know about it. You know the way your code base works, right? So what are these events that the compiler tells you? Well, there are things like, hey, a particular file has been loaded, or here's a declaration of a procedure. It's all been type checked. Here's the syntax tree for the whole procedure, along with all the type annotations, right? Or, hey, we finished compiling the executable. We're about to write it to disk. It's called foo, or we have written it to disk. There's a bunch of other messages that you can get. You can do all sorts of things with this. One of the things that we do is setting the icon for the program, which for some reason people think requires this big IDE and bloated environment that's hard to deal with. In fact, the last time I looked this up, like on the Microsoft website, you could search like, how do I make an icon for my program? And they're like, they don't even have an official solution for it. They're like, download some shady third-party program over here on the web, and it'll build this .ico file, and then you do this automated like .rc file generated thing that goes into your project, and it's all this complicated stuff. And it's like, why, right? So the way we do it is we just have one procedure that your metaprogram can call, called setIcon by file name, and you give it the name of the executable and the name of the icon, and it just puts it in there. It's one line, right? You don't need an IDE to do that. The implementation of this isn't one line because Microsoft makes it harder than it should be. It's probably about 200 lines. But that 200 lines is in a library, and you can just call it with a regular program in the same language as all your other programs, and it's the same on every operating system, and it works great. I mean, this wouldn't work on an operating system that doesn't have the concept of putting an icon in your file. You just wouldn't call it on that operating system, or it would be stubbed out. Okay, so the thing that I want to say is that 80,000 lines per second on a desktop, or 50,000 on this laptop right now, is doing all of this every time. So when I hit that key and it compiled in a second and a half, it read all these messages for all the declarations in this 80,000 line program, searched the whole thing for custom house style. It looked for key map procedures and command callback procedures, and it checked all the print statements. All of this running in a bytecode engine that is not even compiled to native code because your metaprogram runs in bytecode right now. It's doing all this stuff that C++ doesn't even do, and it's still tremendously faster than C++. That's all I'm going to say about that. Okay, so that's one piece of design of this language that I think was very successful, is that metaprogramming system. I wish I could go into more time than that, but it would be like a 3-hour talk just to talk about that. So we're going to move on to a different thing. By the way, there's a bunch of videos on YouTube that go into more depth on all of this that I can refer you to later. One of the other very successful pieces of design, I think, that is different from the way people usually do things is this thing called the context structure, which is just a regular struct with some members in it like you would have in C. But the program passes it around to all your procedures implicitly as an invisible first argument, just like a this pointer in a language like C++. But whereas the this pointer in C++ is only for like localized information about a particular object, this context struct is for all the things that people in common might want to know to coordinate. And it enables a great deal of more coordination, right? So you can add things to the context struct whatever you want in your main program. So you could use it for like thread local storage or whatever. Libraries can add things. But by default, we add some basic members that control memory allocation. So there's allocators, there's loggers, there's, what procedure do you call when an assertion fails? There's what's the index of the currently running thread, so you don't have to do something expensive to figure that out. You can just use that to index arrays or hash tables or something, right? And because this is in a standard place, it enables a great deal of coordination. So if you have a library that somebody else wrote, you've never talked to them, and that library wants to log some information to give it back to you, it just knows how to do that. It can call context.logger with a string, right? Or actually, there's a more convenient function called logprint that's a printf that then makes a string and then passes that to context.logger. And then you, as the main program, are able to plug whatever procedure pointer you want in that logger slot, and you can do anything you want with that string. So it's coordination between you and third-party code that is relatively effortless, right? This also happens with memory allocation. So it is expected in this language that you will override whatever the default allocator is with your own allocator and call some sub part of the program, and that part of the program uses that allocator. You do that just by setting the context, right? So the equivalent of malloc in this language calls context.allocator with some arguments telling the allocator what to do. One of the other things, one of my favorite things actually, it's so simple, but it's so great, is this thing called temporary storage, which also lives in that context. It's essentially just a fixed size buffer that acts as an arena allocator. So if you want to allocate memory out of temporary storage, you just ask for n bytes and it bumps the pointer forward by n bytes and gives you that result. Well, how does that get freed? Well, what happens is the main program just clears temporary storage once per frame if it's a frame-based program, or otherwise, at some point that's known to be safe, where things in the temporary storage won't try to last past that barrier, so like maybe in a message loop or something in a batch application, right? And this enables a tremendous amount of really good stuff. So I can program in a sort of a way that you would in Lisp or in a garbage collected language, but with none of the performance penalties that you get in that kind of language. So maybe I have some procedure called split that takes a string and another string to split it by, and it returns you back an array of substrings. But this version of split just allocates stuff in temporary storage. And so now I can just do very quick stuff like for split this and do something inside the body with each word in the input. Very terse, very fast to write, and very clear. Like I know from looking at this, at least if I look at the definition of a split and see that it returns temporary storage, I know what the lifetime of that is. I don't have to worry about when to free this. I don't have to think about freeing it, right? I don't care. But it's also fast because it's an arena allocator and it never gets explicitly freed. We don't take any of these penalties that you do in a garbage collected language. You don't take any of these like heap random access penalties like you do in C++, right? And then again, you could have done this at any time in any language in just your own code, but the fact that this is a standard thing, it's in the context and everybody knows about it, means everybody can use it, libraries can use it, whatever. So I return strings, like newly allocated strings from procedures all the time. They're just temporary, right? I return arrays from procedures all the time, which is something that I don't really do in C++ very often because it's so painful. Usually in C++ you have the caller like pre-allocate the thing and give you the array and say how long it is. You don't have to do any of that, right? Also, it's more, so a C++ person will say, oh, you could totally do this same thing in C++. You just make a container class that has the begin next methods for the iterator and all that, and then you have standard strings that'll just get allocated and all that, and then the scope of that container and therefore the strings inside it will descope as soon as the for loop is done, and so it'll all work in C++. And it's like, yes, it'll work, but it's a giant mess because the amount of boilerplate code that you need for that is huge, and it's also very slow. You like destroy memory when you do that. It's terrible, right? And so with just this simple temporary storage mechanism, you enable the kind of expressiveness that you would like at a much, much lower cost than you have in either C++ or a garbage collected language. And the reason it's cheaper than a garbage collected language is, again, because garbage collected languages have to figure out if you're using memory or not, and that costs something. Whereas here, we just throw the thing away every frame. We don't care. And so, like I said, since this is a convention, rather than something some programmer is only doing in their own program, everybody can do it. Libraries can do it, whatever. So there's another procedure that I use all the time called tprint, and it's just like printf. You know, here I'm making a string. I sort of take an integer and take the top 32 bits and the bottom 32 bits and make those into separate numbers and say first number dash second number and return that as a string. And I'm just tprinting the pattern and the two numbers. And I don't care how big the buffer is that I'm writing into. I don't care what the lifetime of this thing is. It's just, it's in temporary storage, you know, deal with it. Nobody thinks about it, nobody cares. It's relatively effortless. Now, even with things with longer lifetimes than a frame and much more heavyweight stuff like big tree structures, this can be a very, very helpful pattern if everybody knows that it's a thing that we want to do. So, for example, in this game that I just showed, one of the things we do for one of the effects is we build BSP trees, right? BSP trees are a node-based tree structure. It's a binary tree where you're allocating a lot of nodes, right? And so normally, if you were going to write a BSP tree library, well, okay, I obviously have to allocate the nodes, but then, you know, sometimes somebody wants to free the tree because they don't need it anymore, so you have to go free the nodes recursively. So maybe you would recurse and call delete on the children and stuff. Okay, that's fine. That works. It prevents memory leaks, but it's slow and it creates a lot of fragmentation. So if you're trying to produce a high-quality BSP library, you have to then go and like do a more optimized memory allocator that tries to have more coherency and less fragmentation, right? That's a lot of work, and it's a lot of work to do for every single library, right? Whereas if you have this different convention, which is, hey, I've got some allocator. In this case, it's an arena allocator, but it could be anything. It could be a heap, whatever. I'm going to set that on the context as a default allocator. I'm going to call into you. So you just think you're calling your regular allocator. I know it's my allocator that goes into this specific heap. You can just allocate in your library and never free. Don't worry about it. I'm going to free as the caller when I decide that I don't need the tree anymore, right? So a whole library can just be written that way. And the convention can be just, look, I don't free, you free. And it saves a huge amount of work and a huge amount of code complexity. I was very, very happy when I got to write this way. And it's very fast. So this has just been a couple of things that I'm working on. I mean, maybe it seems a little scattered because there's just so much to talk about. Like I could talk for hours and hours about all the things that we're doing in this language. But hopefully you get a little bit of the taste of it. The roadmap, so far we have not opened it to any users yet. The only users are the 4 people working on the compiler. We're working toward a closed release where maybe we give it out to 10 or 12 people. That originally was supposed to be this summer, but it's going to be a little bit longer because, you know, sometimes things take a little bit longer. So we're going to do that and slowly grow our number of users probably over the course of 2019 as we sort of test the ideas in this language against larger and larger groups of people. And so what's next after this? So like I said, we're doing restructuring and cleanup. We're going to do some more formal library support, make it more enjoyable to control namespaces and more enjoyable to have things that people would normally think of as dependencies. So we have a plan for preventing the kind of dependency problems that you usually get in these languages. We're going to have a structural macro system that's kind of like what you would have in Lisp, but in a language with more syntax. We're going to do a bunch more smaller semantic changes, and especially I'm going to be looking for more conventions like this temporary storage or allocator substitute things that are really, they're not high-tech solutions, right? They're not fancy algorithms, but it makes programs a lot simpler and a lot faster if you can agree on some basic ways of doing things. So that's it. I wanted to leave time for questions, and hopefully we do have time for that. Thanks for listening.
So yeah, we have some time for questions.
Hey.
have you seen what Unity, the game engine, is doing with Burst? Their
Yeah, I've seen that. I mean, I don't use Unity, so it's like not really in the wheelhouse of things that I think about. I am. I hope it doesn't turn into a situation where you're just hoping for magical compiler optimizations to happen, and maybe they do and maybe they don't, right? But I don't know. I mean, I think it's a great step that they're taking to try to make things faster in that way. I hope it's effective. Well, I think it will be effective to some degree. The question is, you know, how effective will it be in terms of increasing the performance of real programs? But I think they definitely, it was a very smart move for Unity to hire Mike Acton, because he's one of the few people who is actually pursuing these kind of ideas about how to make code fast. You know, I just think Mike has a really hard problem, because Unity has established a culture of doing things one way that is kind of inherently slow, and then he's trying to make it faster, and even though he's doing some moderately sized changes, it's not like they're redoing the whole engine from scratch, right? And so the question is, what's going to happen? So we'll see.
My question was going to be if you have a plan to make that sort of automatically SIMD your code.
No, I don't like that kind of approach. I think if you're going to do SIMD well, then you have a programmer who sits down and does it, right? I mean, automatic vectorization, I mean, there's different kinds of things you can mean by that, right? Because the burst compiler that they're talking about is a little bit different from like auto vectorization that a lot of compilers have. When you get toward the auto vectorization end of things, I don't think much of that approach. At the same time, it does sort of, in the average case, give you a constant win. I have a whole talk about why that may not be as good of a thing as it thinks, not about auto vectorization, but about how optimizations that on average are faster by some amount are maybe not that good of an idea. That's for another day. But the plan for right now is actually just to enable people who want to specify things at a low level to do that. So we're going to have intrinsics. We're eventually going to have inline assembly, although that probably won't happen for at least a year. But also, you know, we also try to provide good ways for people to provide SIMD libraries that you can use. You know, but we have to see. That's part of the story that we haven't really done.
Okay, thank you.
Yeah.
Thank you for a very inspirational talk. Strong statements that you made, very interesting, I think. It reminds me a little bit of Braid Victor's work and inspirational talks, especially the inventing on principle. And also you might know of the future of programming. I don't know if you know that talk of Braid Victor. I believe I want to ask this question about the future of programming because you're touching at something that is, we've been, you know, coding in editors for a long time, and your approach is very strong-minded and beautiful, I would say. I want to know what you think of that, the future of programming.
So I like Brett. I think he's on the right team. But I also think that the particular ideas that he talks about are they're not for this domain, right? They're not for building very complicated games. You know, a lot of the things that he talks about how to visualize what your program is doing, they work relatively well for simpler systems. So I think for teaching people how to program and all that, they're great. In the longer term, maybe we'll get to a place where we can figure out how to make visual systems like that scale up and up and up. But you're not going to be writing Assassin's Creed in something like that anytime soon, right? So, but I do think we need more people thinking about that kind of thing and in different ways. That is not the approach that I'm taking. So I'm not doing anything visual here. I do think that visuals are very important. But the way that we're going to approach them is when it comes to understanding your program. So, you know, at some point in the next maybe year and a half, I think we're going to start on, a suite. Our version of an IDE will be more like a suite of things that help you visualize what exactly your program is and how it's changing over time. Like, oh, it's getting bigger. These parts are getting slower. These parts are getting faster. These parts, this part of your code has like more spaghetti and this part has less. And seeing all that very clearly, I think, will help programmers tremendously. And so when I started, one of the things that I said that was a pretty strong statement was, I think 50% efficiency increase is achievable, right? How do you get that? Well, you let programming, you prevent programming from becoming such a disaster in the first place that you end up with all these hard to figure out bugs that take forever to solve, right? And I think program visualization is a large step in that direction. And then the way that we're plugging into that today is we're designing a language that is very good at communicating with the outside world about what your program is through that metaprogram system, right? So that metaprogram and the syntax tree that you get there through the messages is strong enough that you can output the entire program back in text, right? And recompile it again and get the same program, right? And so we have actually a library that does that. So with that much information, but also with type information, right? So you can give that to an editor for highlighting, you can give that to a program understander. So that's what we're building right now is sort of maybe the foundations of that kind of visualization, but it's different from what Brett does.
Thank you.
We don't have time, but we're going to make time for another question. Just another
Okay,
question.
thanks. My answers are long. I'll try to keep it
No. They are very interesting. Who wants to take the last question? Okay.
Hey, mine's very short, no worries.
Yeah.
Actually going to be a couple questions, very short ones, no worries. First one, and this one is probably the shorter one. How are you going to distribute this once it's public? Is it going to be something you charge for? Is it going to be open source? Do you have a plan?
Yeah. No, so it's going to be free always, right? I don't think you can ask people to pay for a programming language. Both the compiler and the game, like we're gonna keep part of the game closed, like just enough that people can't like put it on Android and claim the whole game is theirs. But it'll be like a running game engine that does all this stuff. It's obviously for a specific kind of game. So if you're going to try to make Doom with that, it would be a little different. But it's enough to see how a real game would work and maybe scavenge parts of that code for something different. So that is going to be given out as soon as we can, which is probably with the initial compiler release. When it comes to the initial compiler release, I think we're going to be closed source for a little bit, and then we'll open source it eventually. And the reason for that is just because like open source community management takes a lot of time and energy, and I think we would rather focus that energy on making a good product. Like, even though it's not a commercial product, we're treating it as a product, right? So we want the compiler to be good, we want it to be bug-free, we want it to be fast, we want it to be have a good user interface in terms of the error messages that it gives, when you have a problem. So those are our priorities. And so in the initial phase, as we release to these first people and slowly grow the base, it's going to be probably a binary distribution, but then at some point we'll switch to source because, like, again, you can't ask somebody to build a serious large project in a language if they don't really have the source to it, because at some point you may have a problem and need to solve it, and if it's an opaque binary, that's very hard. So,
Excellent.
Yeah.
Thank you.
Okay. So thank you very much, John, once again. It's been a pleasure to have you here.
Right on.
Thank you all for attending.
Thanks, everybody.